Today I'll be reviewing AP Chemistry Unit 8, Acids and Bases. So let's get started. So what I'm going to first start off with is an introduction to Bronsted-Lowry acids and bases. So what are Bronsted-Lowry acids and bases? A Bronsted-Lowry acid donates a H proton to a Bronsted-Lowry base, which accepts H protons. And so an acid is, under this definition, is a proton donor, while a base is a proton acceptor. And once you have that, you have conjugate acids and bases. So when an acid donates H ion, the resulting species is a conjugate. And this is also true for bases. And you also have empatheric substances, which basically can act as a base and an acid. One example of this is water. This diagram over here shows the reaction with NH3 and H2O to create hydroxide and NH4 plus. And so what you have here is H2O basically donating a proton to NH3. And so its conjugate base for H2O is OH minus. And as the remaining hydrogen is donated to NH3, it becomes ammonium, which is the conjugate acid of ammonia. So now let's go into 8.1, Introduction to Acids and Bases. So basically the reaction with water can create hydronium and hydroxide in an equilibrium reaction. And so there's like an equation for that, which is Kw equals the concentration of hydronium times the concentration of hydroxide, which always equals 1.0 times 10 to the negative 14th at 25 degrees Celsius. This changes when the concentration increases, but in order to find it, you can use the Kw at that other temperature and you square root it to find the H3O plus or the OH minus. So when the hydronium concentration is greater than the hydroxide, the solution is acidic, which is when the pH is less than 7. When the hydroxide concentration equals the hydronium concentration, the solution is neutral, or pH equals 7. When the hydronium concentration is less than hydroxide, the solution is basic, with the pH being greater than 7. And the pH scale. So the pH scale basically simplifies the large molarity values that are shown, such as like 10 to the negative 14th or 10 to the negative 12th. So P is basically the negative log, and pH is the negative log of the H concentration. And if you want to use this in order to find hydrogen concentration from pH, you use this equation over here. And there's a way to derive it, but I don't think we have much time for that. So along with that, you have POH, which I forgot to put in O, my bad. So POH equals negative log of hydroxide, and the concentration of hydroxide is finding 10 times the negative POH. Along with that, you have pH plus POH equals 14. And at other temperatures than 25 degrees Celsius, pH equals POH in water. So we just have a problem over here. Determine the pH and hydroxide concentration of a solution with the hydronium concentration of 5.5 times 10 to the negative 2 molarity. So what you have to do over here is you can go about it two ways. You can find the hydroxide concentration and do the pH by just dividing it by 1.0 times 10 to the negative 14th. Or you could find the pH and then go use pH plus POH equals 14, and then using the 10 to the negative POH, then you could use it to find hydroxide concentration. So I'm going to do what I just talked about, the latter. And what I'm going to do is I'm going to do pH, and I'll show my work over here. So pH equals negative log (5.5) times 10 to the negative 2. So let's use a calculator to plug that in. So negative log 5.55 times 10 to the negative 2 would equal pH of 1.25. Now what you have to do is you have to use 14 minus pH so then POH will equal 14 minus 1.25, which is, I believe, yeah, 12.75. And using POH, we can use OH minus equals 10 to the negative 12.75. And that would be and that will be 1.77 or actually 1.78 with rounding. So 1.78 times 10 to the negative 13th. And that will be our answer. So, all drawings. And as temperature increases, Kw increases. And so the reaction basically shifts in order to form more product and consume the reactants. And temperature favors an endothermic direction, so the autoionization of water is endothermic. So estimating pH values, this is like a useful trick during MCQs. So what you can do is you can basically estimate it to the first degree, like before the decimal point, because in order to estimate, in case like you have one of those multiple choice questions in which you can't use a calculator. So what you have to do, so let's say 8.45 times 10 to the negative 10th. So negative 10th is the absolute, is the power. And so what you have to do is you have to use the absolute value of negative 10, then subtract it minus 1. So 10 minus 1 equals 9. And so you can estimate it as 9 point something XX. But then most of them will not have it be like two numbers in 9 as their answers. So you can just make it as 9 point something and then get whatever is the closest answer. So that's a useful trick, and I would recommend trying it out as long as like it works for you. If you have any other ideas on how to estimate, then please link it in the comments below or talk about it. So 8.2, pH and POH are strong acids and bases. So the thing with strong acids and bases is that they're assumed to dissociate completely unless the question indicates otherwise. And here's the 7 strong acids, which is HCl, HBr, HI, HClO4, HClO3, HNO3, and H2SO4. But that's only the first H in H2SO4, so it creates HSO4. So weak acids are under equilibrium, while strong acids and bases dissociate completely. And so along with that, you also have strong bases, which are LiOH, NaOH, KOH, calcium hydroxide, barium hydroxide, and strontium hydroxide. And these bases, so with the group 2 bases like calcium hydroxide, barium hydroxide, and strontium hydroxide, the hydroxide concentration after dissociation is twice the original base molarity, as there's 2 hydroxides, not 1. And the group 2 bases will have a higher pH and a lower POH due to having a higher molarity. because there's more hydroxide with the group 2 bases than with the group 1 bases. 8.3, weak acid and base equilibria. So weak acids and bases, they basically ionize to a limited extent, and hydrogen does not get removed as much with the strong acids and bases. So you have Ka, which is the acid dissociation constant or the acid ionization constant. So it's like an equilibrium constant of its own in order to find how much A or acid is dissociated. And you could use ice table to find the concentrations of hydronium or hydroxide using the Ka and the equilibrium constant. You also have percent ionization, which measures the strength of an acid, and you can also use Ka times Kb equals Kw in order to find either Ka or Kb from the other values. So let's try this problem with an ice table. So the pKa for lactic acid is 3.86. It's asking us first to calculate the Ka for lactic acid. And what we first need to know is the formula for lactic acid. So the formula for lactic acid, wait one sec, there's the annotation. Okay, so lactic acid is C3, my bad. I don't memorize my lactic acid. So you have C3H6O3. And so you have the pKa, so you can use 10 to the negative pKa. To calculate Ka. So then you use 10 to the negative and just plug that into a calculator. And you basically get a Ka of 1.4 times 10 to the negative 4. Now it's asking us to determine the pH, so I'll just delete whatever I don't need. So what you have over here is what you have to do is you have to first have the equation. So C3H6O3. Yeah, that's right. 1 plus H2O and so what you have to do is it then creates, I believe, yeah, C, as it's an acid, it creates H3O plus and C3H5O3 minus. And what you have is you have 0.20 molar solution. So that's the initial molar, and you can cross out the H2O, which you will not need. And so you have 0 concentration of hydronium approximately and 0 concentration of C3H5O3. So what we have to do is you have to have like a variable in order to find H3O and C3H5O3. So you can subtract like from X minus X and plus X plus X. And so it'll be 0.2 minus X equals X. And then you have to use the acid dissociation equation, which is Ka equals H3O plus and C3H5O3 minus, forgive my bad handwriting, and C3H6O3. So now we have is 1.4 times 10 to the negative 4 equals x squared over 0.2. And you can take out the x over here as the amount of hydronium, or the amount of x will be negligible, so you can just cross out the x. So you can multiply both sides by 0.2. Sorry for my sister. She is trying to talk to my parents. Times. 1 second, please. Sorry about that. Just need to tell my parents to and my sister to be quiet. And so what you have to do now is you just have to square root 0.2 times 1.4 times 10 negative 4. And you then get x, which you just plug into the calculator. So square root 0.2 times 1.4 times 10 negative 4. And that will be 5. And with this, you can just basically, then you could use the pH. So pH equals negative log of this, because you already have the hydronium concentration. So pH will equal, so use a calculator to figure this also. And pH is 2.28. So that's pH for lactic acid. And clear all drawings, and then let's go on to the next one. So 8.4, acid-base reactions and buffers. So you basically have an acid plus base makes a salt and water. So you have to use dilution, which is M1V1 equals M2V2. And in order to get M2, you have to add up the volumes for both reactants in the reaction to get the total volume. And this requires like a lot of planning. So I'll go over one of these problems. So what we have over here is a 20 milliliter sample of 0.2 molar HBr solution is titrated with a 0.2 molar NaOH solution. And so what it's asking us is to calculate the pH after 15 ml of NaOH was added. So what we first have to do is find the amount of moles of HBr and the moles of NaOH. So let's do it for HBr. So 0.02 0.020 liters times 0.2 molar. And that's 4 times 10 to the negative 3 moles. And you also have moles NaOH, which is 0.015 liters. times 0.2 molarity, which is 3 times 10 to the negative 3. So now what you have to do is you have to do a before and after table. So this basically with the HBr, you can use it to find the H plus. So moles of H plus because there's no ratio. And for any OH, you can use this to find OH minus. So H plus OH minus creates H2O. And you have, so before and then after. So before, what you have is 4 times 10 to the negative 3. And before for NaOH is 3. And so you subtract that, so you get 0 because OH is a limiting reactant, and you get, oh, you have 0 over here and 3 and to negative 3. And H, you subtract 4 times 10 to the negative 3 from T, 3 times 10 to the negative 3, and you get 1 times 10 to the negative 3. And then now that you have like what happens after the reaction, you have to use this and you have to divide it by the total volume. So you have 1 times 10 to the negative 3 moles H plus divided by 20 ml plus 15 ml, 35 ml or 0.035 liters. And that would give us a molarity of 0.0285. Now you have to calculate pH from that. So H equals negative log of this, and pH will be 1.54. So that's how we do it. So clear all drawings, then let's go into 8.5, acid-base titrations. So you have basically around a few different types of titrations. So the first one is a strong acid and strong base titration. So in a strong acid and strong base titration, at the equivalence point, which is basically the point where the amount of titrant is greater than the amount of titrated solution. So basically what happens at that point is it'll be the pH will be 7 because in the strong acid and strong base, the H plus and the OH minus completely neutralize each other out at that point. In a weak acid strong base solution, then the titration curve will have the titration be more basic, as there's more of the conjugate base than there's the acid itself. And at half equivalence point, you can use the pH to calculate pKa. So for this one, the pKa is at 9. So sorry, pKa is around 9. Sorry, pH is about 9, and it's at 25 milliliters. So you can divide 25 by 2, which is 12.5, and you can find pKa somewhere around here. This is a weak acid titration, and this is a weak base titration. And for a weak base and strong acid titration, basically what happens is that the equivalence point will be more acidic. So it'll be at like 6.0 or something around that. So here's like a diagram of all the titration curves, and yeah. 8.6, molecular structure of acids and bases. So the strength of an acid depends on a number of factors, the most important of which is the molecular structure. So the ability of an acid to ionize. So the stronger the bond, the weaker the acid, and it takes more energy to break the bond. And if the bond is highly polarized, which is a large accumulation of positive and negative charges on the atoms, the acid will tend to break up more. Hydroxylic acids. So in the halogen column, so the most strongest acid is HF, then it's HCl, then HBr, then HI. So due to the higher bond energies, due to the higher electronegativity, HF has the highest bond energy, so it's a weak acid because it takes so much more energy to break. But then HCl, HBr, and HI have lower bond energy, so they're much more stronger than HF. And by strong acids are acids that dissociate more. So oxoacids. So oxoacids or oxyacids. So they contain hydrogen, oxygen, and one other element as a central element. For example, HNO3, HClO3, and HBrO3. So they have a presence of one or more OH bonds, and the more electronegative an atom is, the more acidic the solution will be, or the more it dissociates. And so oxyacids have an atom bonded to one or more oxygen atoms, sometimes with hydrogen atoms attached. And so you have the inductive effect, which is the attraction of electrons in adjacent bonds by more electronegative atoms. So acids such as nitric acid experience this effect. Polarity in the molecules draw electrons away from the hydrogen atom, which makes it easily ionizable. So for example, you have nitric acid, whose conjugate base, nitrate, is more stable or weaker due to the negative charge being spread evenly across each resonance molecule. Electronegative elements tend to stabilize the conjugate base relative to its conjugate acid, and so they increase acid strength. And the greatest electronegativity is the strongest atom, which dissociates the most. 8.7, pH and pKa. The relative concentration of an acid can be determined by predicting the pH to its pKa. If the pH is less than the pKa, the acid has a higher concentration in the solution. If the pH is greater than the pKa, the conjugate base has a higher concentration in solution. So indicators. So weak organic acids or bases that change color in their unionized or ionized forms are indicators. And so what indicator you use is dependent on the type of titration. You can determine by seeing where the equivalence point is and by finding the indicator that is closest to that equivalence point. And along with that, you have the endpoint versus equivalence point. So the equivalence point basically is when the number of moles of titrant is sufficient enough to completely react with the number of moles of titrated species. The endpoint is when the indicator goes under its color change. So they're two completely different things, so don't mix them up. 8.8, properties of buffers. So a buffer is basically a solution that is resistant to a change in pH upon addition of a strong acid or base. And there's 4 ways to make one. So you can either neutralize part of the weak acid with a strong base. You can neutralize a weak base with a strong acid. You can add a weak acid with the salt of the conjugate base, which is stronger. Or you could have a weak base with the salt of a conjugate acid, which is also stronger. And a buffer is basically a special case of the common ion effect. So let's try this problem over here. So the pH of solutions of 4 acids prepared at various concentrations were measured and recorded in the table above. The 4 acids are in no particular order: chlorous, hypochloric, lactic, and propanolic acids. A 25 ml sample of 1 molar solution of acid 1 over here is mixed with 25 ml of 0.50 molarity NaOH. Which of the following best explains what happens to the pH of the mixture when a few drops of 1.0 molarity HNO3 are added? So what you can first take out is the pH of the mixture stays about the same because the hydroxide ions in the solution react with the H3O. So the thing is that the conjugate base is not hydroxide's not the one which we're trying to see because there's not much these reactions do not have hydroxide in them, the dissociation reactants. So we have to use the conjugate base to determine. So you can, hey, I messed that up. So you can basically just cross out D. D won't be the right one. Along with that, you have the pH of the mixture increasing because HNO3 is a strong acid. The thing wrong with that is the pH would decrease because if it's a strong acid, there would be more hydrogens that dissociate, and when there's more hydrogens, the pH would be lower. So A is wrong because, well, it's wrong. The pH of the mixture decreases sharply because H3O ions were added. But then that won't be true either because it's a buffer and it's between the acid and its conjugate base, not between the HN3. So the best one, in my opinion, would be C, as the pH stays about the same because the conjugate base reacts with the added H3O ions. 8.9, the Henderson-Hasselbalch equation. So you can use the Henderson-Hasselbalch equation to qualitatively and quantitatively analyze buffers. So when a conjugate base and conjugate acid concentration are equal, the log is gone, and so the pH will equal to pKa. When the conjugate base concentration is greater than the acid, the pH is greater than pKa as the log is positive. And when the acid is greater than the conjugate base concentration, pH is less than pKa as long as negative. So for solving problems like this, you have to choose the Ka value that would be closest to the pH that's shown for the buffer, as that is shown in some problems that they may give. 8.10, buffer capacity. So a buffer should be able to control its pH after the addition of reasonable amounts of acids and base. So increasing the concentration of the buffer keeps the pH as the same, but increases amount of acid or base, as the buffer can neutralize as long as the ratio remains constant. So the number of moles of acid and base, the conjugate base, determine the pH, and diluting will not change the pH. So how do you solve problems like this? You have to choose an acid with the Ka close to the intended value of H concentration, and then you have to use Henderson-Hasselbalch, and adding more base or acid with the same ratio will keep the buffer the same, but will increase the capacity, while adding less base or acid with the same ratio will decrease the capacity. So here's the problem over here. So to prepare a buffer, so the equation above represents the base ionization equilibrium for ammonia, NH3. To prepare a buffer with a pH of approximately 8.20, 3.5 grams of NH4Cl should be added to 500 milliliters of 0.01 molar NH3. The buffer is accidentally prepared using 85% pure NH4Cl instead of 99% pure. And assuming impurities in the solid are unreactive, explain how this error affects the pH and capacity of the buffer. So since there's less NH4Cl compared to what is required to do the buffer to have the capacity be done, then there'll be more NH3 than NH4. So the pH will be higher. So pH increases. So along with that, the capacity of the buffer will not be gone by using the amount of NH3 and the ratio, but it'll be determined by the amount of NH4Cl. So you can basically, it'll work better with NH3, and it'll increase the capacity for base, but not much for acid. So that's our answer. So I guess that's it. So I hope you all do good in the AP test and on whatever other tests you may have on the subject. And I hope you all stay safe. Thank you.